Hey, this is Venki in Lab 3, Magnetic Field of a Bar Magnet. So the purpose of this lab was to understand distance dependence of a magnetic field using a small bar magnet, a magnetometer, VPython, and Biot-Savart law, and other equations. So using the magnetometer phone app, I measured the on-axis magnetic field at various distances from the small bar magnet, and with this data, I created a logarithmic plot. And with this plot, I calculated the distance dependence and compared it to the Biot-Savart law, and I also calculated the magnetic moment. And with the magnetometer, I also calculated the magnetic field from 45 degrees away from the small bar magnet, and I compared this measurement to what VPython calculated. So some results include distance dependence, or n, was negative 2.985. Magnetic moment, mu, was 2.392 amps times meter squared. And then the 45 degrees axis magnetic field was this in Teslas. And we'll see later how these compare to the theoretical values. So some concepts include Biot-Savart law, and this is the equation for the magnetic field of a dipole on axis. And then this distance dependence of a bar magnet, which can be simplified to k times r to the n power. And when you take the natural log of this equation, you get that right there. And this is important in determining our experimental values, as you'll see later on. So some assumptions include in Metz, France, the magnetic field is roughly 48 microteslas, and that the bar magnet acts as a magnetic dipole. So I first downloaded the Tesla meter magnetometer app onto my iPhone and determined where north was so I could lay the ruler down away from interferences and align it east to west. Then I placed the magnet at one end as seen here. Then I determined the location of the magnetometer sensor in my iPhone. And then next I took 3 measurements of distance and magnetic field from the magnet that produces the magnetic field of 20 microteslas in the x component. And then I repeated this for various distances. And at a 45-degree axis, I took 3 measurements of distance and magnetic field from the magnet that produced a magnetic field of 100 microteslas in the x component when the phone was on axis. So this spreadsheet averaged the 3 measurements for each of the different distances. So for the on-axis measurements, it produced a natural log graph, and this line of best fit, the equation, will be important later. And for the off-axis, I got 9.26 e to the negative 6 for the x component, 4.00 e to the negative 5 teslas for the y component, and I got this by subtracting the earth from the measured due to the way the dipole is facing. And for the z component, you could assume it's 0 because we neglect the magnetic field that's pointing out of the phone. For the calculations, you could take the equation of the line we had earlier, and its slope is n. So I got negative 2.986, and then its y-intercept is ln of k. And with this, you could solve for k to get 4.783 times 10 to the negative 7th. And knowing k and n, you could set the equation for Biot-Savart law of a dipole to the distance dependence of a magnet. And then you could rearrange to solve for mu. And once you rearrange and plug in your knowns, you get that mu is 2.392 amps times meter squared. So in the code, I put in my value for mu, the magnetic dipole of 2.392. And then over here, the code creates magnetic fields at two observation locations on axis and 4 observation locations perpendicular to the magnet. It also creates a magnetic field at a location of 45 degrees, the same distance that I used in the experiment of 0.1706 meters away from the magnet. So the white block is the dipole representing the small bar magnet. The orange arrows are the on-axis magnetic fields. Our magnetic fields look at observation locations on axis, and then the blue arrows are the magnetic field at observations perpendicular, and then the green arrow is the magnetic field at 45 degrees with a small bar magnet. So you can see here that the orange arrows are pointing in the same direction as the dipole and are twice as big in magnitude as the blue arrows, and then that the blue arrows point in the opposite directions of the dipole because they're perpendicular. And then for the magnetic field at the 45 degrees, I got this. So some questions to answer is that So some observations that I noticed is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, but as it moves closer to the magnet, it measures the magnetic field in the x component increases. So if I hadn't oriented my experiment to compensate for the magnetic north, the logarithmic graph would look the same, but there would be different values for for the x component of the magnetic field, and this would increase the difference between the experimental and theoretical values. If I had stuck two identical magnets together end to end, then the magnetic field measurements would be stronger or greater in magnitude. So for my distance dependence of n, I got negative 2.985, which is very close to the theoretical value of negative 3. And then for my 45 degrees axis magnetic field, you can see that my experimental values are pretty close to my theoretical values, but they're not exact. And this may be due to how there could be other interferences acting on the magnetometer in my iPhone, or that my magnetometer in my iPhone is just not as accurate as it should be. And that's all. Thank you.